Thank you for taking time this morning to be with us so we can have this common experience with this webinar, CFD Misconceptions and Common Pitfalls. My name is Doug Hatfield, and I'm going to be your host for today's session. With me is Jim Bungener. Jim is a senior application engineer here at Flex Compute, and Jim will be presenting the content that we'll discuss today. By way of background, Jim is a master's in CFD from Princeton. He spent 10 years designing racing yachts in the America's Cup circuit. And then he moved from racing into the eVTOL market and spent another 10 years there with one of the customers of Flex Compute, Whisk, before joining Whisk as a joining Flex Compute as a senior application engineer several years ago. He's been using Flex Compute and Flow360 almost since its inception. So we're lucky to have him on our staff and part of our team. For a few housekeeping items, what we would like to propose is that please put any questions you have in the Q&A section of Zoom, and we'll capture those so that we can have Q&A at the end. And the panelists will be tracking those questions so that we can have 10 or 15 minutes to review. So with that, I'd like to hand it over to Jim and let him begin the webinar. Thanks, Jim.
Thank you, Doug. So let me start out with a brief introduction to Flex Compute for those of you who don't know the company. So the company was started based on three key concepts. The first one is to leverage all of the great advances in hardware that we've seen over the past few years. And then you combine that with the latest, greatest coding techniques, coding softwares that have evolved recently, and you create synergies. You optimize the hardware for what the software can do. You optimize the software for what the hardware requirements are. And by doing that, you create great synergies of efficiency where your calculations happen to a whole lot faster. Another key concept was to address common pain points of the CFD industry. So with these three concepts, we've created what we call a new CFD ecosystem. It's based on the cloud, and it has many benefits. One of them is you can get started in minutes. You send us an email, create an account, you can be doing CFD. You interact through our ecosystem through a Python API, which you can link as part of the chain of your whole CFD. So whatever CFD process you have, just link in that API in the middle of that chain, and it'll drive our servers remotely. If you want to just run a specific case or just dabble your toe in it, you can use our webpage. It's also a very good place to look at specific cases in detail. So you launch a batch run with the API, and then you go and look at a specific case through the web page, analyze the results, understand more about your solution. It offers the ultimate flexibility. If some days you have no CFD to run, doesn't cost you anything. If the next day you have an entire database to run, you send it to our servers, we will deal with it. So it really allows you to cater your CFD production to whatever your demand is. We, as part of that pain point, we pride ourselves on an industry-leading customer support service. So the idea is we want to give you a relevant answer in as fast as possible so that you can go back to being a productive CFD engineer. This is along the same line. We want to you only pay for successful cases. So if your case diverges, if your case something happened, you do not pay for those results. We want you to be successful, and this is sort of our promise to you. You will generate good results. One of the other advantages is you have no hardware to buy and maintain. As part of that get started in minutes I spoke about earlier, you don't have to, stay abreast of all the latest, greatest hardwares, maintain, updates, all of that stuff. We do that for you. The goal is we want to remove as many of those things that make CFD complicated away from your plate so you can go back to doing what you love, as in do proper CFD. One of the other advantages is that synergy I was telling you about earlier between the great hardware and great coding techniques is the speed benefit. So now by sending all of that information through our pipeline, you can get steady state simulations in minutes. And by that, I mean industry relevant simulations in minutes. Trends in simulations, hours or less. Have an entire database with thousands of points, give it to us. A day or so later, you'll get your answer. So this productivity is, we feel, a great asset to to being able to get answers and generate results. The other interesting thing that's happened is to fully use those synergies, that new tool, that new CFD ecosystem. It requires renewed imagination by you, our users. It's more than just bigger meshes, fast to run. There's so much more we can do, and we can now start looking at more complex scenarios like dynamic derivatives or full-on acoustic studies, complex optimizations. And we regularly have customers coming up with some very interesting setups, which just a few years ago would have not been possible because it was just too expensive, too time-consuming, too complicated. So now it's very cool to see all of these new ways and innovative ideas that are coming out of this new tool. So with that, let me move on to the subject of the day. So I'm going to have 4 key sections. First one is to be wary of comparisons. I'm going to bring an example of a CP plot versus force coefficients. And then I'm going to discuss the value of a good mesh size study. Combine that with the importance of proper convergence. And then I'm going to try to give my 2 cents to that age-old question of how accurate should simulations be. And then I'm going to finish with a little reminder of the resources we have available to help you get answers to your questions, conclusions, and then the Q&A. So with that, let's start comparing CP plots versus force coefficients. So here I've come up with a simple scenario. We have a simple 2D NACA 0012 section. I'm going to run it, or I have run it, on 2 different mesh densities. And let's assume these are 2 sources of information. And to that, we're going to simulate the CFD comparison and validation process. So you can imagine that, say, one of those data is wind tunnel data, the other one's a simulation, or one of them is one software versus another software. And so if you look here, that's the NACA 0012 at alpha 16 on 2 different meshes. And you can see that the CP plots look very good. The comparison looks exceptional. And so you'd be able to, you'd be allowed to think, wow, the simulation really matches the wind tunnel, or those 2 codes really match each other. But if you start looking in details, you can see that if you zoom in here, the CP plot is actually significantly different. If you look at the trailing edge, there's differences. And because the forces are the integration of those pressures, you actually end up with something that looks like this, where this is the CL alpha curve, and it looks fine until you get to that alpha 16 point. And this curve now, the comparison doesn't look anywhere near as good at all. So the moral of the story here is that until you have seen a comparison that shows you the data that you care about, you really have to take comparisons with a grain of salt. The key concept here is, for a lot of us, we're interested in forces and moments. So get comparisons that compare forces and moments. CP plots are great, but they can hide a lot of differences within 2 seemingly identical plots. Let me do a quick segue to introduce this eVTOL geometry. So we created that using a CSM script. It's a script that's through a tool called ESP. It's an open source software to generate CAD. So this geometry was generated parametrically, and ESP, the beauty of it is that it generates CFD ready CAD. We fed that through our automated meshing tool chain, and then we added BET disks. You can see the 4 disks in the front to simulate the propellers, and then we have 4 more disks in the back here, creating thrust downward. And so the idea is we now have a representative eVTOL geometry to go and test with. So I'm going to use that geometry to show you the value of a good mesh size study. We see a lot of clients not willing to invest in a good mesh size study, and it's always, I believe, a shortcoming. A good mesh size study is really, really useful. So with a proper mesh size study, mesh sensitivity study, it's a perfect example of scope creep, because you start out with a very specific question, and then the more you learn, the more questions you end up with. So it's quite important that at the beginning, you set yourself some hard limits as to how far you're going to get this, you're going to take this study, how precise you want it to be. And but it should include surface mesh as well as volume mesh variations. And one of the beauty is that it will give you a sense of the accuracy of results. And so this idea, which I will touch on later, by doing variations, you can see how much the variation in inputs, as in meshes, gives you variation in outputs. It's the age-old competition between mesh size, runtime, and costs. So that is something that you have to keep in mind always, obviously. And remember that finer is not always better. That's where engineering judgment and experience comes in. And a lot of that experience can come from more mesh sensitivity studies. But the beauty of it is that it will lead you to a better understanding of the relevant flow physics for your case and what sort of mesh requirements you need to capture said physics. So not only will you learn about what meshes are good, you will learn about the specific flow features that you need to capture. You will also understand better the simulation pitfalls, as in which cases in an entire database converge well, which cases take forever to converge. So you'll have a better understanding of the magnitude of scope of what you're trying to accomplish. For this presentation, I'm just going to do, for the interest of time, a quick boundary layer growth ratio study. So here's our eVTOL geometry on the right. I'm going to use the same surface mesh for my 4 different cases. What I'm going to vary, same surface mesh and the same Y plus value. What I'm going to vary is the boundary layer growth ratio. So ultimately, we have a fairly fine mesh at the top, boundary layer growth ratio of 1.1. So each cell, the distance normal to the wall, is 1.1 times the previous cell's height. Growth ratio here, 1.2, so I'm growing faster. 1.5, I'm growing fairly coarse. 2.0, I'm very coarse. So that's the only difference between those 4 meshes, is how fast my boundary layer cells grow. And then I'm going to look at the metrics of importance to me for this particular example, forces and moments. So one thing we see happen regularly is this thought that my Y plus 1 mesh, I have a mesh of where the Y plus is around 1, which means it's a good mesh. Not really. It is a necessary but not sufficient condition. You can see all of my meshes here have a Y plus that's even less than 1, and yet we will get very different answers. So these are the CL alpha curves for those 4 different meshes. And you can see that in the linear regime, things match fairly well. And then as the angle of attack starts increasing, the physics start getting more involved, more interesting, differences start to happen. But the key concept here is that assuming I'm interested in this, what I'm going to call the cruise regime, the pre-stall linear regime, the purple dashed line and the green dashed line, which is my finest growth ratio of 1.1 and the previous one of 1.2, have the same answer. So the idea there is I keep on refining growth ratio of 2, growth ratio of 1.5, growth ratio of 1.2. I'm still seeing significant differences. I keep going. Growth ratio of 1.1. Now I've got the same answer between 1.2 and 1.1. So I know that my 1.2 captures the physics in as much as this mesh sensitivity study can say. So the idea is you keep on refining the mesh until the answer stops changing to within the bounds that you have set yourself before you started this mesh sensitivity study. And then the idea there is to get confident that, okay, this mesh is capturing the physics. I don't need to go to the very fine mesh. I can stay at the one before. So you can see here at alpha 14, which is after all those meshes start diverging from each other, the very different flow patterns. So at alpha 14, we're highly separated for growth ratio for the finest mesh. For the next finest mesh, the flow is attached. And then the next, coarsest mesh. The next coarsest mesh after that, the flow is still separated. Now, I think we can all agree that my chord-wise distribution of points is not high enough to capture the physics. But the point here is that you can get very different answers by doing mesh sensitivity studies or looking at the mesh. So another thing that I wanted to go into is on the importance of proper convergence. So this is that same eVTOL we were looking at earlier, and I'm running it at alpha 11, and I'm running it for 3,000 pseudosteps. And you can see the residuals are dropping. It's nice and steady. We're getting to fairly low residual values. This looks very good. I'm happy with that convergence. I look at the forces. The forces have stabilized. My lift and drag are looking good. I would say I am confident in the quality of my results here. Now, if we look at this plot, it's again my CL alpha curve. The idea there is that the dashed line is the results I just showed you above, where I run for 3,000 iterations. And then I run it for another 7,000 iterations. And we look at the differences. And all of these are steady state simulations, same mesh, same case setup. The only difference is 3,000 versus 10,000 iterations. And you can see that at alpha 11, so before alpha 11, we get the same answer. That's comforting. At alpha 11, things start diverging. And what's going on here is that at alpha 11, we are starting to have significant flow separation. And remember, this was a steady state simulation. Steady state no longer represents the physics accurately. We have multiple correct converged solution. And so by forcing this time varying phenomena into a steady state solution, we are actually asking, we're not being really honest with ourselves, and we're asking too much out of that steady state simulation. And it's trying to give us the solution, knowing that there is more than one solution. So it is oscillating between these different answers. You can see it here. That's the same simulation done in a time-accurate manner. And you can see the variations in lift and drag as that separation bubble on the trailing edge of the wing moves around. So the idea there is to properly look at your forces and their force convergence to make sure that you are not capturing, you're not averaging a time accurate phenomena in a steady state fashion in a way that does not make, that varies through time. And now suddenly when you're comparing two cases, one case could have been stopped here, another case could have been stopped here. You've got differences, or you seem to have differences between two different configurations that are actually due to your modeling technique. This is something to keep in mind. Last but not least, how accurate should simulations be? And that's a very difficult question to answer. But one of the things to keep in mind is, how do we know if we're accurate enough to be of value? So the question is, in order for my, let's take that eVTOL example again. In order for my eVTOL, for my answers to be of value, how close do they have to be? Do the consumers of the CFD data, as in, let's say the guidance people, or the structures people, or the power and performance people down in your team, what sort of accuracy do they need? So one of the idea is to translate those CFD results into a metric of interest. Let's say you're talking to a pilot, and you're telling him or her that the CL difference is a CL of 0.1. Well, if we look at our eVTOL airplane earlier and we look at the CL alpha curve, in cruise, our DCL D alpha is 0.1. So for every change, for every angle of attack of 1 degree, we get a 0.1 change in CL. So now, instead of saying I have a CL difference of 0.1, you could say it's equivalent to an alpha difference of 1 degree. And now the pilot is being given information in a language that they understand. You could transform CD difference into pushing prop RPM, or your propeller RPM. CFX is very similar to CD. You can also translate it into propeller RPM. CFY, your side force, you could translate that into beta. You could tell the pilots, here it's the difference between these two codes is so many degrees of side slip beta. CFZ is similar to CL, related back to alpha. Your moments, your 3 moments, CMX, CMY, CMZ, you should relate to control surfaces. So for example, for your rolling moment CMX, related to aileron deflection. So you need to calculate your dCMX, d aileron deflection derivative, and transforms those CMX values into aileron deflections. You could translate it into stick inputs if you're talking to that pilot. So the difference, imagine a conversation along the lines of, the difference between these two curves is this many inches or centimeters of stick movement. And now they can visualize how big or small their variations are. For CMY, relate that to elevator deflection, and for CMZ, elevate that to rudder deflection. So going back to the point earlier about mesh sensitivity studies, if you make the effort ahead of time to think about what units, what words the people that are going to be looking at your CFD results think in, and what they're used to seeing on the data, and you transform your CFD data into those that language, then you can go to them and say, how accurate do you need me to be? And that can be used as a metric back into your mesh sensitivity study, fed back into your sensitivity study, until you can decide, or that allows you to decide how close your answers need to be. So if you go back, for example, to our mesh sensitivity study here, you'll notice that the difference between each one of those lines is 0.2 in CL. That's equivalent to 2 degrees alpha. Does your pilot really fly within 2 degrees of alpha? Maybe, maybe not. But now you can get a sense of the difference. Initially you thought, well, I'm going to run at a growth ratio of 1.2. maybe actually I can just get away with a growth ratio of 1.5 because my pilot can't tell the difference between the blue line and the green line when he's flying. Or maybe even a growth ratio of 2. So that's why you need to sort of back out from your CFD data the metrics of interest to the consumers of the data. One last thing here. So right off of our Flow360 flexcompute.com website, we have a resources tab that contains a really great amount of CFD essentials lectures. And those give you insights into how to properly do CFD simulations. Some of them deal about turbulence models and what turbulence model conditions you should use under what type of flows, how to simulate isolated propellers, how to simulate eVTOLs, all sorts of different scenarios are explained and discussed. So that's always a good place to go and find out more about how to do proper CFD. We also have right on that flexcompute.com page a documentation page. And in there, you'll find lots of examples of different realistic scenarios and how to run them properly. We also have a knowledge base, which deals with a lot of the questions that we see coming across our desks from users, and we've tried to answer them. And so there's a lot of really useful knowledge there into what values to put where, how to properly do a good CFD simulation. With that, let me leave you with a few key points. To beware of comparisons with an agenda. It's very easy to hide fairly significant differences inside plots. Try to find comparisons of the metrics that matter to you. And this is a key part. Think about what is good enough, and then try to find comparisons that give you the kind of information that you're really after. Always relate your CFD results accuracy to the metrics of interest. There's no need to simulate an airplane to within 0.01 CL difference if your pilot can't even tell the difference. And get confidence in your results by doing a proper mesh sensitivity study. You'll learn a lot about the flow features, where the vortices are, which are the interesting areas of the flow field, and get answers about how much you can rely on the CFD simulations, where do the CFD simulations behave well, where are they more difficult to run. So there's always a lot of information that can be garnered from a proper mesh sensitivity study.